Welcome back to part 4 of our work with equilibrium. We have discussed what equilibrium is. Equilibrium is when the rates of the forward and reverse reaction are equal. It does not mean we have equal amounts of products or reactants. That's one of the most common traps students fall into. Don't let that happen. Okay. So, forward and reverse reaction rates are equal at equilibrium. We've discussed how we can find if we're at equilibrium by calculating Q. What if we were at equilibrium and then we as the outside experimenter do something to that equilibrium to mess with it? Well, the short answer is we're no longer going to be at equilibrium. We're going to be at a Q. So we would then have to calculate, okay, so if I get this reaction at equilibrium and I add in some more reactant B, what's going to happen? And you would then have to calculate a Q and see how Q compares to K and which way is going to go faster or slower in order to get back to equilibrium. Well, here's good news. We have this principle that Le Chatelier came up with, and I'm sure I'm not saying that name right because my tongue does not speak French, but there's probably some more syllables in there than I'm saying. But Le Chatelier's principle tells us that when we change an equilibrium, it will predict for us which direction, forward or reverse, is going to go faster for a while to get back to equilibrium where it was before, get back to that equilibrium number. Okay, now this is going to be true for any time we change anything other than temperature. Now here's the thing, if I change temperature, yes, I will get to equilibrium. It will not be the same equilibrium number. Changing temperature changes the actual number of K. Any other changes we do, pressure, volume, more of this, less of that, that would all be the same K value, but not if we change temperature. We can still predict what's going to happen, but it's not going back to the original K number. So just be aware of that when we talk about Le Chatelier's. So let's do a lot of examples, and I want to show you a visual example of how this would work.
When a system at equilibrium is disturbed, reactions or changes of state that reduce the stress are favored. For example, if the temperature is increased, endothermic reactions which absorb this energy or phase changes that result in molecules with more kinetic energy are favored. After the initial response to the stress, a new equilibrium is established.
Notice changing
If
temperature
pressure is increased,
made a new equilibrium.
reactions that result in the fewest moles or the lowest volume are favored.
Notice
By reducing the volume
smaller
of particles
volume
in the system, the
means
stress of
smaller
having
amount of
increased
stuff to
pressure is
fill the
relieved.
volume.
A new equilibrium is then established. Similarly, if the relative concentrations of reactants and products are changed, the original equilibrium is disturbed.
So
When, for
notice how
instance,
they
product is
remove
removed,
products.
the system establishes a new equilibrium by producing more product.
We try to make more products so
If
that we have
continue to remove
4
product, the
gaseous
system will
products at a
continue to
time.
respond until there is no more reactant. Chemists use Le Chatelier's principle as they examine the dynamics of systems and work to optimize them to obtain the maximum yield at the minimum cost.
Okay. So very, very useful, especially in engineering, to understand how Le Chatelier's works. It works extremely well even on large scales, like if you're doing chemical engineering. So let's do another example. Maybe. There we go.
Le Chatelier's principle states that a system in equilibrium that is subjected to a stress will react in a way that relieves the stress. Some of these stresses include changes in pressure, changes in concentration, and changes in temperature. Consider this reaction of nitrogen and hydrogen to form ammonia. A change in pressure affects only equilibrium systems in which gases are involved. If the pressure of a system is increased, the equilibrium will shift to favor the reaction that produces the fewest moles of gas. This action will reduce the total pressure of the system. In this example, more ammonia is produced to reduce the pressure on the system.
So check it out. Pressure only affects gases.
Reagents also affects a system. If the concentration of one of the reagents is increased, the equilibrium will shift to favor the reaction that reduces the concentration of the added reagent. If more hydrogen is added to this flask, more ammonia will form to reduce the hydrogen concentration. A change in the temperature of a system can also stress a system. Reversible reactions are exothermic in one direction and endothermic in the other. According to Le Chatelier's principle, the addition of heat shifts the equilibrium so that the reaction that absorbs heat is favored. If heat is added to an endothermic reaction, the equilibrium shifts to favor the formation of the products. If heat is added to an exothermic reaction, like this one, the equilibrium shifts to favor the formation of the reactants.
Okay, I do point out we have to go back to our first semester, remembering that right here, okay, check out the signs. A negative joules amount would be it is exothermic, heat's exiting, and a positive joules amount would mean it's endothermic, heat is entering. So be sure you keep that in mind. Okay. I'm sure you got rather confused by those pictures, but that's all right. You haven't practiced the Chatelier's yet. I wanted you to see the visual nature of what we're trying to show. Okay. Roughly, Le Chatelier's principle tells us which way a reaction will shift. And that's the actual words we use there. We'll say that it will shift. Now we're meaning it's going to go forward or reverse, but sometimes we take a shortcut and say it'll shift to the right, meaning the arrow pointing right will be faster, or it's going to shift to the left, meaning the arrow pointing to the left will be faster. So be aware of that. You can say shift to the right, shift to the left. You can say shift the forward reaction more, shift the reverse reaction more. You can say favor the products, favor the reactants. There's many ways to say this. As long as you say the correct one, you probably will get your points on the test, right? So, again, we're dealing with is Q less than K or is Q greater than K? But the good news is we don't even need a calculation for Le Chatelier's. If a stress happens to a system that was at equilibrium, it had to first be at equilibrium, and then we put some sort of outside stress on it, it's going to shift to favor the way in the reaction that will minimize that stress. In other words, it does the opposite. Okay, so let's give this a try. Here's my reaction. Now notice first off, I've got two reactants, I've got two products. All my reactants and products are gases, which is why we're going to discuss pressure. If they weren't all gases, pressure would leave the solids and liquids alone. Pressure would only affect the gases. Notice also, on the left side in the reactants, I have a total of 5 moles of gas. Maybe like that. And then on the product side, I have a total of 3 moles of gas. All right. Pressure is increased. If we increase pressure, what effect does this have? It is increasing pressure is like taking the container and making it smaller. Okay. That's not what we're doing, but that is what it's like doing. Okay. So increasing the pressure, how will the equilibrium shift? The equilibrium would shift to fit into a smaller area better. If you increase pressure, like imagine just squeezing a sponge. If you increase pressure, what's going to happen to the gas? Imagine having a balloon in your hand and just squeezing it smaller. What's going to happen? It's got to fit into a smaller space. So increased pressure is going to favor smaller amount of moles because smaller amount of moles fits into a smaller space. Smaller amount of moles in this reaction is the left side. Wow, I said that backwards. Right side, because 3 is less than 5. So equilibrium will shift. We could draw an arrow. We could say shift to the right. We could say favor products. We could say use up more reactants to make more products. We could say all those kind of words. And quite often just an arrow pointing in the correct direction is enough. Now, why will the equilibrium shift? If I'm making more products and less reactants, That means, I'm just going to doodle here, concentration of, okay, there's my thought doodle. Okay, I would do that in the margin of my paper. If it's got to shift to make more products and less reactants, then it's got to be that Q was not big enough yet. I need Q to get bigger, more numerator, less denominator. So it shifts because Q was less than K. Or remember my tip? If you write it this way, and I was about to mess that up. If you write it this way, you can then, check your work by drawing the arrow, and that should match your answer there. If you always put K on the left. Q was less than K, so the forward reaction has to go faster in order to catch up to equilibrium. Okay, what if pressure's decreased? Well, that's going to give it more room. It's like stretching my balloon bigger and letting the gas inside have more space. Okay, so it very much is like taking my container and making it bigger. That's not exactly what's going on, but it's a great way to think in your head about it. Again, 5 moles of gas on the left, 3 moles of gas on the right. What would fill a larger container better, 3 or 5? Please tell me 5 moles. So our equilibrium is going to shift to favor that. We would say it's a shift to the left. We could draw a left arrow. We could write the word shift to the left. We could write shift to use up products and make more reactants. We could say lots of things. As long as you're indicating it correctly in terms of the direction, you've got it. Why will the equilibrium shift? Again, I need my little mental doodle. Okay, this I would write on the test once when I hit the first question and just flip back to it every time that I need it. But I am making the reactants bigger and the products smaller. That means Q is getting smaller. So if Q must get smaller, Q was bigger than K. And check it out, I can check my work with my little, oh yes, my arrow needs to point that direction in the reverse. Okay. Since Q was small, must have been larger than K, Q needs to be getting smaller, and that's how we can figure this out. 5 fits into a larger box better. To make 5 moles of gas, we had to shift to the left. By shifting to the left, we can infer that Q was greater than K. It has to get smaller. Q's number has to get smaller to get back to equilibrium. Okay. Volumes increased. Well, gee, if we haven't kind of already had this mental picture, we definitely have this mental picture. And we still have 5 moles of gas on this side and 3 moles of gas on this side. Now let me state, what if I had 5 moles of gas and 1 mole of solid on this side? I would totally ignore the solid or the liquid. When it comes to pressure and volume, you only look at gases. Did you catch that? For pressure and volume, you're only looking at gases. Okay. So how will the equilibrium shift? Well, I need to fill a bigger box, so it's going to shift to the left. Why will it shift? Because Q was greater than K. How did I know Q was greater than K? Because of the doodle I did earlier, or I'm like, oh, my arrow goes this way. Check out that sign. My K, if I always write it on the left, and my Q, if I always write it on the right, is got to match. Okay. That's a little, tip to help you remember these. If that doesn't work for you and you'd much rather go back to the doodle, please, please, please go back to the little doodle. Because this is truth here, definitely. This is simply a shortcut to get you to the same answer faster. But that only works if you remember to write your K on the left and your Q on the right. What if volumes decrease? So I had a larger box, now a smaller. What fits better in a smaller? The 3 moles of gas, not the 5. So it's going to shift to the right. Why will it be shifting to the right? Well, check out. There's K, there's Q. My sign goes that way. Oh, look, Q was, after shrinking the volume, Q became less than K. So it's going to shift to the right to make more products, but use up more reactants to make Q equal K. Now, explain why pressure and volume can only affect Kp and not a Kc. Why can we not use Kc? Because Kc is concentration in molarity. That's moles per liter. That means something dissolved in something. That means something in liquid form or aqueous. And again, pressure and volumes will only affect gases. So it has to be really a Kp, or just, we'll say K in general, and that works just fine. Okay. What changes would affect Kc? Well, anything that would affect moles or liters could affect Kc, absolutely. Let's try some. Okay. Here's my same reaction. Check it out. I've got my gases. I still have 5 on this side. I still have 3 on that side. That really is not important anymore. But my concentration of A is increased. What effect will this have? Here's where that like going in the opposite direction thing fits in. I'm adding more reactants. If I add more reactants, the equilibrium wants to get rid of the extra. How do you use up reactant? By making products. Which way will the arrow point to go faster from reactants to products? Because to use up reactant A, it's going to go make more products. It's going to shift that direction. Again, if I add in more A, I'm like, here's a syringe with some more gas A. I'm going to poke it into my flask and squirt the extra gas in. That makes, for a moment, that's going to make more reactants. How do I get rid of that more reactants? I want to make, the reaction will want to make more products with it. That will minimize, don't know why that wasn't writing, oh, because it was off the screen. Make more products. That will minimize the effect of more reactants, is to kind of use it up. That's the opposite, if you will. I added more, it's going to make less. To make less of a reactant, it has to make more products. It has to shift to the right. What's that tell us about our K and our Q? Well, here's officially why the equilibrium shift. By adding more of A, my Q became less than K, and so I'm going to have to make more in order to use it up. Okay, what happens if we decrease A? Somehow I have a magic syringe that I can stick in and only remove A. Now, I say that, and that's a silly way of saying that, but there certainly could be a way to remove A, and that is by reacting it with some other side reaction inside the same vessel. So what effect will this have? Well, if I'm decreasing A, that removes reactant. What's the opposite? It's going to make more reactant. How is it going to be able to make more reactant? Turn what used to be products back into reactants. That would be a shift to the left. Why is that? Because Q, when I added more A, became greater, sorry, when I removed A, became greater than K and needs to now get back to K. Again, if you need that little doodle, products over reactants, if I remove A, I'm making the denominator smaller there. When I make the denominator smaller, that makes the fraction larger. So Q became greater than K, and we'll need to shift to the left, shift from products to reactants, use up some products to make more reactants, all the same ways we're saying the same thing there, in order to reach equilibrium again. Okay. What if D is increased? What effect will this have? Well, D is increased. We now have more product. What's going to be the opposite? We're going to use up product. How do I use up product? Take products and make reactants out of it. The reactant's going to shift to the left again. Why will the equilibrium shift? Well, it will shift because Q was greater than K. What's that mean in terms of my doodle? Those are concentration brackets, by the way. That means, check it out, if I increased D, I have more of my numerator, whatever that was there, which means it's a larger number. larger fraction. So Q became greater than K for a while. It's going to shift. It's going to reverse. The reverse reaction is going to run faster for a little bit until it can get back to K. What if D is decreased? What will that do? Well, that removes product. So what's it going to do? It's going to make more products. How do you make more products? Shift to the right. Why will you shift to the right? Because Q was less than K. It made for a moment my numerator smaller, and therefore my overall fraction was smaller. Therefore Q was less than K. And so the forward reaction is going to proceed faster in order for me to get to equilibrium again. Okay. Why would catalysts not change equilibrium? They like to ask this question, or within like a series of questions, of which of the following would not be affected by a catalyst, which of them would be. Okay, why would catalysts not change the equilibrium? Well, let's talk about that. What's our definition of catalyst? It's two parts. It might be involved in the reaction. It could be involved, but it is unchanged. So it starts as a reactant and ends as a product. Okay, you don't use up the catalyst. Also, it increases the rate. Okay, that's our definition from kinetics. It remains unchanged, so it's not used up, and it increases the rate. The rate of which way? Forward or reverse? Okay, pop quiz. Is it going to increase the forward or reverse? If you said both, you are correct. A catalyst will increase both rates. Remember, back when we mentioned catalysts, we were talking these hill diagrams, and we said a catalyst is going to make a shorter hill for the reaction. Is that a shorter hill for the forward, or is that a shorter hill for the reverse? Well, hopefully you said it's shorter for both. In forward, it only has to go up this hill, and in reverse, it only has to go up this hill. Now notice it doesn't change whether it's endothermic or exothermic. It changes the amount of activation energy. It will not change the equilibrium at all, ever. Because equilibrium is about the rates being the same, and it's the same size hill. It's a shorter hill, but it's the same size hill for both rates. So please, please, please don't miss that question on the test when you get to that question. Okay, why would the addition of inert gases not change the equilibrium? Okay, well, inert gases do what? Right, they don't do what is what I should ask. Inert gases don't react. So if I have a balloon and I fill it with helium, well, let's go with nitrogen. Nitrogen can react. I fill it with some nitrogen, then I fill it with some more helium. What's that actually do to the nitrogen that was in that balloon? Please tell me nothing. Okay, because remember, our model of gases is that, like, here's nitrogen. I throw in some helium. There's helium. Maybe here's some more nitrogen. Gases are so far apart to begin with, I have plenty of room to squeeze in more gases in order to get them to, I can throw in nitrogen and helium and xenon and all I want, and there's plenty of room for them to all coexist in the same balloon. Will that increase the pressure overall? Absolutely, but that's not a pressure increase that does anything to our reaction. The only pressure increase would be to the reactants or products in the reaction, and most certainly an inert gas would never be in your reaction. So they ask this one a lot. Adding an inert gas would not change anything about the equilibrium, because it's not the pressure total that would change whether or not you want more moles or less moles. It's whether the pressures of the individual reactants or products will change it. Okay, so please see that correctly. Now, what effect does changing the temperature have on equilibrium? Yeah, changing the temperature will have an effect on equilibrium because it changes the equilibrium. Not changes it to Q and it gets back to equilibrium. It makes a new value for K. What can we do with the Le Chatelier's principle? We can detect whether, or we can predict whether the new K is going to be greater than or less than the old K. That is absolutely something we can do. So let's do some practice of that. Here's a reaction, and what do you notice? Hopefully you're like, oh, we never had that heat term before. Heat is a product, meaning this reaction is exothermic. Heat will be produced in this reaction. Temperatures increase. I'm making it hot. Hot, hot, hot. The reaction doesn't like it. That's like adding more heat. Oh, it is adding more heat. That's exactly what's happening. I am adding heat if I increase temperature. What's it going to do? That's the opposite of that. It's going to try to use up heat. How is it going to use up heat? Make this side of the reaction reactants, make this side of the reaction products, shift to the left. Use up that heat as you use up D and C to make A and B. Shift to the left. Why will this equilibrium shift? Again, it's not going to be a discussion of Q versus K anymore. It's now a discussion of we have a new K, and what is that new K going to be? Our K old, okay, and then we have our K new. All right. And if we're going to be making, let's bring in my doodle, concentrations. Okay. Yes, I know I'm not like squaring them or tripling, or what would that be, quadrupling them, but I know I don't have the exponents, but that's okay. It's just a doodle. So we're shifting that way. We're going to be using up products. We're going to be making more reactants. My new K is going to be bigger. My new K is going to be greater than my old K was. All right. So that's what's going to happen. My new K, my new equilibrium, is going to be at a number bigger than my old K is. How much bigger? I don't know, but I know it's got to be a bigger number. Same equation now, temperature is decreased. Well, if I decrease temperature, I am removing heat. So what's that going to do? We want to make more heat. How do I make more heat? Make heat a product, shift to the right. Why would I do that? Because K old is going to, or sorry, K new is going to be less than K old. And again, if you pull in your doodle, I am making more products using up reactants. This is going to be a bigger number than it was. So K new, did I say that backwards? I'm making more products using up reactants. That's what I've said, right? Yes. So K new is going to end up greater than K old. Wow, I did that. No, I didn't want old there. K new. Okay, so K new is going to be greater than K old. More products, less reactants. That makes me wonder about the previous one. K new. Absolutely. Wow, I did that one wrong. What do you know? K new is going to be less than. I don't know why I saw that and thought it would not be a smaller number. K new is going to be less than K old was. Okay. Now again, it's not a Q, it's a K. And it's a new K because we're messing with temperature. That didn't work. Come on, there we go. Okay, if we want to do the shortcut like we did with Q and K, you have to write it always with the new K on the left and the old K on the right, and then your arrow and your greater than, less than sign will match. That would certainly be a good shortcut there, if you can't just figure it out on your own from a little doodle. Okay, check out what's changed. Now heat's on the left side and temperatures increase. This will increase the temperature is more heat. So let's use it up. Shift to the right. What's that mean? Okay, more products, less reactants. More products, less reactants. That's going to be a smaller number. K new is going to be less than K old. Temperature's increased. More heat. We're going to use it up. More products. Why did I draw my arrow that way? I am having a very dyslexic day. My apologies. And I don't have you in class stopping me when I do stuff like that. Okay, let's try that one more time. Okay, so more products, less reactants, a bigger number. K new will be now greater than K old. And see how I've been self-checking myself with the way the greater than equal sign goes and the way the arrowhead points. It's a great thing to do on the test to be sure you're doing it right. Okay. All right, same one as before, but now temperature's decreased, so we are removing heat. So we need to make more. That would be a shift to the left. Now on my doodle, that means more reactants, less products, because I'm using a products to make reactants. I'm going to get this right, I really am. Less of a number. So my K new compared to my K old is going to be less. Okay, very different form. Or is it? But they could easily, and they probably definitely would show it this way on the test. Some kind of sort of this way. So you need to know how to deal with this. This is definitely something to handle. What's the positive delta H enthalpy tell us? Please tell me, tells us endothermic. Now, as you've already witnessed, my brain flips things way too easy. And so I need to guard against that. And I'm glad I've been catching it all along, which is why I like those little tricks of things lining up. But it's going to be endothermic. So I like, once I know it's endothermic, I like writing the word heat over the side of the reaction that it's on. Endothermic must mean it's on the left side. Exothermic would mean it's on the right side. Okay, now let's actually answer the question. Temperature is decreased. I have less heat. How do I make more? Well, since heat's on the left side, I'm going to make more. Heat's on the left side, it's going to shift to the left. What's that mean between my K's? That means that my K new is going to end up less than my K old because, going back to that little doodle, we're going to lose products, make more reactants. That's going to be a bigger number. Well, I don't know why I said bigger number. A smaller number. I even tried to say that, and I don't know why that didn't work. Okay, now what do we have? Well, we have something that looks the same, except now it's negative. What's that mean? Please tell me exothermic. That means I want to write heat over here. Okay, so now temperature is increased. That means I have more heat. How am I going to get rid of more heat? I'm going to use it up. How do I use the right side as reactants if my arrow points that way? So my equilibrium is going to go faster in the reverse direction for a while. It's going to shift to the left. That's what we say. We just say shift to the left. What's that mean about my equilibrium? Okay, I'm going to try this one last time and see if I can not flip it. We have less products. We're going to get more reactants. That's going to give me a smaller number. So when I compare my two K's, my new K is going to be less than my old K was. Woohoo, I actually got through that. Okay. All right, we have lots of practice to do with Le Chatelier's. It's an extremely useful technique, but I'm out of time for this particular segment, and that's a really great introduction to just the concept of Le Chatelier's principle. They will have those type of concept tests over Le Chatelier's all over the multiple choice. Well worth knowing what's going to happen. Super huge, great predictive tool. Going to be very useful for all the rest of the semester. It will be on the test several places in several forms. Be sure you're very well familiar with the concept. And then come back for the next video, and we will actually look at some numerical work with Le Chatelier's. Good luck on your practice.